It's simple to visualize data in 2 or 3 dimensions, but machine learning problems usually involve many variables, which makes visualization difficult. Often there's an internal structure to the data, which means that most of the information is actually contained in fewer dimensions than the whole original data set. This means that it's possible to transform variables into a lower dimensional space without losing much information. For reasonably small problems, it may even be possible to visualize the transformed data in 2 or 3 dimensions to get an approximate representation of the data. Principal component analysis and classical multidimensional scaling provide 2 ways we can transform our data so that we can then potentially reduce the number of dimensions. Both methods can be thought of as building a new orthogonal coordinate system, where the coordinates are ordered in terms of importance in some sense. In PCA, the coordinates are in order of how much variance in the data they explain. In multidimensional scaling, they are in order of how closely they preserve the pairwise distances between observations. PCA always transforms an n-dimensional space into another n-dimensional space. Multidimensional scaling transforms an n-dimensional space into the smallest space necessary to preserve the pairwise distances. Note that multidimensional scaling can be used with any distance metric. If we use the usual Euclidean distance, multidimensional scaling actually gives the same result as PCA. With both methods, we can get a measure of the importance of each dimension in the new coordinate system. This is typically visualized with a Pareto chart, which shows each individual value as a bar, with the running total as a line. We can use this to determine how many dimensions we consider sufficient to obtain a reasonable approximation to the full data. If 2 or 3 dimensions is sufficient, then we can plot just the first 2 or 3 coordinates of the transformed data.